Good morning. Time for more rotational motion. Yes, more rotation. So last class, we had spent the whole class looking at rotational kinematics. What are rotational displacements? What are rotational velocities? What are rotational accelerations? And I hope things started to kind of fall into place. We said that one of the best ideas for studying or for setting up problems is, kind of put the linear kinematic formulas in front of you and then look at the angular ones and try and make the one-to-one analogy here of how the linear quantities and the angular quantities, they're analogous, right? There is this very tight analogy going on between them. We had looked at a number of examples. The formulas we have here are just for constant acceleration, so I don't want to say these are completely, these are limited to constant acceleration. But that's pretty much all we're going to look at in this course, so this should take care of us. Now we had looked at a number of examples, and we got to this last example with the kinematics, and we had run out of time, so let's pick that up now. It says that we have a centrifuge. So this is a biological centrifuge, or a biological lab centrifuge, where the idea is to take some kind of a biological sample. You know, you've grown a lot of bacteria, or you've grown a lot of yeast or something, and now you want to lyse those, the cell walls or the cell membranes, and separate out the different materials that your yeast or bacteria have been producing for you, and try and isolate those materials. And you can do that with centrifuge. So centrifuges will separate objects out based on their densities. And with a really high speed centrifuge, that can be done in a reasonable amount of time, I guess. So anyway, our centrifuge, the specifications for ours, is that it rotates at 20,000 RPM. That sounds pretty fast. And it accelerates from rest to this value, and it only takes 30 seconds. So it spins up to its 20,000 RPM speed in just 30 seconds. What is the average angular acceleration? And then it says how many revolutions has it gone through during the time it was picking up speed. I like that question, right? Because well, it's kind of like when we were accelerating before, just asking how far have we traveled. And if I want to, going back to our formula here, this is constant acceleration, or we can treat it as constant. They say assume a constant acceleration when they say what's the average value. And so we're going to be using, well, let's see, maybe this formula. A couple different possibilities here. This is relating how fast we're going compared with the acceleration. We'll use that to determine what the acceleration is. And then these have displacements. So we want to be able to go in and say, during the time it was picking up speed, how far did it travel? And by how far, we mean what angle did it travel through? Okay, it's a good problem. So let's set everything up. Here's my centrifuge. There's the axis of rotation right there, right in axis on that point. And then I put a test tube over here, and actually they're metal containers, so they're these really sturdy metal tubes. And I put the samples in there, and I put them on each side of the rotor so it would be balanced. Turn on the centrifuge, and it starts picking up speed. Now, what they told us was, well, when it's at rest, it's at rest. And the omega naught is 0.0 radians per second. But when it's picked up to top speed, that is at 20,000 revolutions per minute. And look, it's our friends, the conversion factors. So 2 pi radians equals 1 revolution, and 1 minute equals 60 seconds, and the revolution units cancel, the minute units cancel. It worked out to be 2,094 radians per second is the speed that it tops out at. So I am using one of my formulas for constant acceleration. If you go back to that table, the ones that we looked at, alpha is equal to omega minus omega naught over t. So it went from 0 to 2094 radians per second in just 30 seconds. And that's giving us an acceleration of 70 radians per second squared, 69.8, if we keep three significant figures. So we're using all of these constant acceleration formulas because they said go ahead and just calculate average values. Well, if it's just maintaining an average value throughout, that's constant. So we're going to go ahead and assume constant acceleration. Now I'm picking up that second equation that we pointed to and saying, hey, theta naught, that's 0. Omega naught, that's 0. So the distance that we travel, now that's an angular distance, is going to be given by 1/2 alpha t squared. So I'm putting in my 1/2. I'm putting in the alpha value, and the alpha value that we calculated in part A is that the angular acceleration is 69.8 radians per second squared. And then the t squared is here. So it said it took 30 seconds to bring this up to speed. And so I'm plugging into that 1/2 alpha t squared equation. And putting everything into that, I ended up with 31,000. So this stuff is conversion. I got 31,410 radians. So I did everything in standard units. Now, it turns out on a problem like this, I didn't need to because everything is angular. The alphas are angular, the omegas are angular, the thetas are angular. So I could have done the whole thing in rotations or instead, but I went ahead and converted everything to radians. I think that's good practice in converting units. But now I'm going to convert them right back. So I started out with doing everything in radians, converting everything. I got my alphas in radians per second squared, and I got my thetas in radians. But now I can say that one revolution, or one rotation, is equal to 2 pi radians, and I ended up with 5,000 complete rotations. So during that 30 seconds, it went around 5,000 times. Okay, so it's a good example for making use of these formulas for constant rotational accelerations. All right, we're moving on. So we did all the kinematic stuff, and we said today we were going to be looking at rotational forces. If you think back, once we had finished all of kinematics, we finished chapter 2, we finished chapter 3, all the kinematic stuff was done, and then in chapter 4 we introduced force and we introduced mass. So what we have to do now is we have to introduce rotational force and rotational inertia, rotational mass or rotational inertia. So first of all, let's look at the force. To make an object change its rotation, it's true if it's at rest, to get it started, we have to apply a force. Now, if it's already moving and we want it to rotate faster, we have to apply a force for that too. Anytime we want the angular velocity to increase or decrease, we've got to apply a force. Now, if there's no friction, and I have an object and it's spinning, and there's no forces acting on it, it just keeps spinning at the same rotational velocity. So that's handy to think about too. In any case, let's get a force in there so we can get an acceleration. It says that it's not enough to have a force acting on something. Now this picture's a little, what they've got is they've got the edge of a table or something. So here's a table edge. And then they put a hinge right here. And then they put a table extender is what I'm, oh, it's a door. Oh, I finally am getting it. Okay, it's a door. It's a top view of a door. It's so obvious now. Did they say it's a door? No, because anybody looking at it can see this is a door. It's a top view. This is the doorknob. This is the doorknob. I actually was wondering, I was actually saying to myself, why didn't they just use a door as an example? But they did. I didn't pick up the picture, and it's such a good picture. So here's the door. It's the wall extender, it's a door. There are the doorknobs. We're looking from the top down, and that is the rotational axis. That is the hinge. That's the wall. So the wall, door. Now what we're going to do is, when you walk up to a door, where do you push it from? Do you push it from over here, or do you push it from here? Where do you want to push it from? And you go, well, I push it where the doorknob is, and the doorknob is over on this, so let's get rid of the doorknob. Why did they put the doorknobs over there? Why didn't they put the doorknobs in the middle? I've watched all those Hobbit movies, right? And the Hobbits put their doorknobs in the middle. Why don't we put doorknobs in the middle of our doors? The Hobbits do. Let's see. Torque doesn't depend just on force. It depends on lever, or lever distance, or lever arm. So what happens is, when I walk up to a door, I'm sure you tell yourself this every time you walk up to a door. You walk up to a door, you observe the hinges, and you go, I want this door to rotate. I want this door to go into rotational motion, because if the door rotates, I will be able to walk through the doorway. So that's what I always think when I come up to a door. So here's the doorknob, and I'm walking up to the door, and the torque is the product of the force times the lever distance. Now the lever distance, or lever arm, is measured from the hinge out to where the force is being applied. If we apply the force farther away from the hinge in a perpendicular direction, that will give us the most torque. That will make rotating the door as easy as possible. So I only have so much force to work with. Let's make the lever arm bigger so that we get more torque. Go ahead and try it with a door. I mean, try pushing it from a point near its hinges, and then push it from out away from the hinges, and you'll know why they put the doorknob out there. Those poor hobbits are only getting half the torque that they would be able to get if they just take those doorknobs and move them to the position farther away from the hinge. All right, so these are going to be our lever arms. Those are going to be forces, and torques are going to be the product of the two. I am so glad I finally recognized that's a door. That is so weird. Okay, here's some other examples. And so here's a tire, and they've got the the dust cap screwed on there really tight. So they got a little tool down in there to help remove that, and that's an axis of rotation. So what they're doing is they're applying a force, but notice they've got some leverage. They've got a lever distance, so here's the axis, and the application of the force is at a good distance away from the axis, so they'll have more leverage. I think the pipe wrench is even more obvious, I hope. Let's see, what are they doing with that pipe? It is threaded. Okay, that's good. So you can see the threads here. I was going to say, if it's soldered, that's a real problem. So this is threaded, and they're trying to loosen this, it looks like. Now, if they just put their hand on the pipe and try and rotate it, it's really hard to unscrew a pipe. But with a pipe wrench like this, getting lots and lots of lever distance, see, all the way from axis of rotation is right along the center of the pipe. So there's an axis of rotation, and the lever distance is measured from the axis of rotation out to where the force is being applied. Now, the force needs to be ideally in a perpendicular direction to get as much leverage, to make use of that leverage as best possible. So let's go back to the door. I am so glad I realized this is a door. So here's a top view of a door. There's the hinges. And what would happen if we walk up to the door and we push it this direction? Well, if I push this direction, look where the force is pointing. The force is pointing right to the hinge, and that tells me that I'm not getting any lever distance at all. I'm getting 0 lever distance if the force is pointing right to the hinge. What if I push in this direction? And you guys probably are saying, well, yeah, that's how doors operate, because you're getting the most leverage. Now, what about this one at this funny angle? What if I push it at an angle? Well, if I push it at an angle, that force is going to have a useful component that's perpendicular to the lever distance, but it's also going to have a component that's kind of not helpful, pointing right towards the hinge. So in general, if we have a force acting along some direction, what we can do is we can create the line of force, or the line of action for a particular force. If we continue that over to where the hinge is located, we can then draw a perpendicular distance from the hinge out to the line of force, the line of action. That is our lever distance. So for that, if I want to calculate what the lever distance is, I can do a diagram like this. Now you can do a diagram like this, which I always feel like requires trigonometry, maybe doing a sine or cosine here or there. I actually think it's easier to say, what I can do is take the force itself and divide it into perpendicular components and parallel components, and then I just ignore the parallel components, because they are not going to provide any torque. And torques are able to create rotational accelerations. So for this door, which is at rest, if I wanted to start rotating, I need a rotational acceleration, I need a torque. All right, so I think that's what they're showing here too, is that one approach would be to take the force and draw a line of axis. Here's where the axis, oh look, it does say axis this time. Axis is right there. Lever distance is that perpendicular distance, but I think the easier way is to, they're defining torque here, so they're going to use a symbol tau. It's a little tau, they should make it bigger. So torque should be really big, because torque's like a really cool name for a physical quantity. And it should be at least as big as the R and the F. Anyway, so what they're doing is they're doing a full lever distance out to the point where the force is located, and then they're only taking the perpendicular component. So if they only include the perpendicular component, that's an easier, I think, an easier way to do problems usually. But either way it's equivalent. Either way is going to work. Let's try this out. So we have a cylinder here. We have a compound wheel, and here is the axis of rotation. So the axis of rotation for this is right at the center, and this wheel is able to rotate around that axis. Now, the wheel is a compound wheel. It has 2 different regions with different diameters that have been, I don't know, welded together or something. So we've got 2 disc-shaped wheels, 2 cylindrical wheels of radius 30 centimeters and 50 centimeters, and they're attached to each other. They're placed on an axle that passes through the center of each. Calculate the net torque acting due to the forces shown. So let's take a look at the forces and let's ask about what's going on here. So see force A right there. So force A is 50 newtons. That's about 10 or 12 pounds of force. So here's 50 newtons in that direction. Now, how much of a lever distance will that force have? And it looks like, because the force is placed tangential to that circle, to the cylinder, is placed tangential to that, we can take the entire force, 50 newtons, and we can say that it has a lever distance of radius A, and distance A is 30 centimeters. So I can take force A, multiply it by RA, and that's how much torque. Now, FA, is that a positive torque or a negative torque? And what am I talking about? Well, torques in one direction, we're going to want to call positive, and then torques in the other direction, we're going to want to call negative. So, are these 2 torques working together, Do I want to add these two torques or do I want to subtract them? And these two torques are opposing each other, right? If we use a standard convention, rotations in this direction would be positive. That's like this is the x-axis and this is the y-axis, and these are positive angles. And then these are negative angles, so that would be a negative rotation. But again, it's up to you in a problem which direction you call plus and minus. But you got to remember, if the torques, you've got to be able to identify if the torques are working together or are they opposing each other. Now, for force B is tipped at an angle. So what they're doing is they're setting things up so we can take components. So we can say that there's going to be a force B cosine of 30 in this direction, and there's going to be a force B cosine of 60 in the other direction. And so this force, the vertical component, that's not giving us any torque at all. That force lines right up with the axis. Imagine having this wheel, this compound wheel, on an axle, and then walking up to it and attaching a cord or something and pulling it in this direction. It's not going to make it rotate. So what about in this direction, tangent to the edge? And you go, absolutely. That's what I want to do, is I want to get as much force as possible acting tangentially. Well, we're kind of stuck here. They've given us 50 newtons, but it's not here. It's tipped at an angle. Now let's see. Force B is tipped at an angle, so we only get part of that. On the other hand, it's got more leverage. It's got a longer lever distance. So let's do the calculations and see which one of these torques is going to win out, or if they exactly balance. It's possible the two torques exactly balance, so there's no net torque. All right, I hope this looks like the picture. Oh, look, I wrote in the axis. Excellent. So the axis is right here. It's kind of confusing now with that arrow. Get rid of that arrow. This is force 1 acting here. So R1, the lever distance, is 0.30 meters. It's 50 newtons. They are already perpendicular to each other. I can take the entire 50 newtons times the 0.30 meters of leverage, and that gives me 15 newton meters. We decided that was going to be called the positive direction. Now, R2 is 50 centimeters, but we're only going to get the cosine of 30 component. That angle right there, that theta, is 30 degrees. So I'm only going to get 30 degrees on that, and so the force component in the x direction, I only get to use 43.3. I don't get to use the full 50. I only use 43.3. Now, remember, force 2 has more leverage. So that's going to be 0.50 meters. And when I calculated this, torque 2 wins out. Torque 2 is force 2 times R2, and that's 21.7 newtons times meters. And those are units for torque. And so it looks like torque 2, oh, this is torque 1. Oh my gosh. Okay, that needs to be a 1 right there. So torque 1, this is still torque 1. Sorry about that. Cross that out, put a 1 in there. That's torque 1 and it's 15. So torque 2, it turns out, is 21.7 newtons times meters, and it's in the negative direction. So the net torque is in the negative direction. I can add those two torques together, and it's 6.7 newtons times meters. So this thing is going to start picking up speed in this direction, because if I have a net torque, which I do, then I can calculate what the acceleration, the angular acceleration, is going to depend on what is the net torque, and then what is that capital I down there is something we're going to learn about in a bit here. It's called the rotational inertia. So I got to find out what the rotational inertia is, but I'm going to take my net torque and divide through by that rotational inertia. All right. Now, a couple things we should point out here. First of all, again, this is tau 1, so that should really be a 1 right there. Torque has units of newtons times meters. Now, we've already seen newtons times meters before. That was when we defined energy. Energy had units of newtons times meters, and we called those joules. So what about torque? It's clearly a different physical quantity. Torque is not the same thing as energy, and yet it has the same units. You know, when I learned this in my freshman physics class, I couldn't sleep for a week. I just kept thinking, how is that possible? How could you have two very, very different physical quantities, but they both have the same set of units? Finally, I just accepted that that's what happens sometimes. So for torque, we're going to leave the units as newtons times meters. And leaving the units as newtons times meters reminds us that a torque is always a force times a lever. So it's a force times a lever distance. And for energy, we're always going to use joules. So we'll always switch over into joules whenever we're looking at energy. And so the units, you know, we can keep them distinct. All right, so let's take a look at a little bit of rotational dynamics. So we've introduced torque. We can see what torque is now. And now we're going to introduce something called rotational inertia. Let's see what happens. So knowing that accelerations are caused by forces, so the force needed to accelerate an object with mass m is equal to the mass times the acceleration. That's how much force we would need. What we can do from this diagram is say, all right, a torque would be the force times r. So we could take this expression, m times a, and then we could multiply by r. And then what we can do is go, but instead of using a linear acceleration, let's use a rotational or angular acceleration. A then is going to get replaced by r times alpha. So what we've done here is, for the torque, we've said we need to take the force, multiply the whole thing times r, and then we're going to take out the a and replace it with alpha times r. That leaves me with two factors of r. So the torque required to take an object with mass m and keep it rotating around this axis is equal to m times r squared times alpha. Okay? So if it's not accelerating, I don't need any torque. If this is part of a rigid object, so let's say there's an axis of rotation, this is some type of a rigid connector, then the force from the connector will keep it in circular motion. And if there's no friction, there's no air resistance, there's no resistive forces going on, then this object will just keep rotating around forever. It's only when I have an increase or decrease in the speeds or a redirection of the rotational axis when I require a torque. Okay, so a lot of times, those examples we saw before, a lot of times when we get out the pipe wrench, something's at rest and we need to get it to start moving. That's going to require an acceleration. If it's a door and I want to walk through the doorway and the door is currently at rest, I need to create, momentarily, not for a long period, but I need to create a little rotational acceleration so that it will get out of my way so I can walk through the doorway. So those actions require a torque. And now we can see it's not just the mass that makes things heavier rotationally, it's the mass times r squared. So m times r squared is what we call the rotational inertia. Okay, I've got that down at the bottom and I got it highlighted, and I've highlighted this net torque. So the net torque that I'm going to need depends on how much rotational inertia I have and what kind of acceleration I want. Now, if you think of how much resistance there is to acceleration, let's think about this. If I have my arms close to me and I'm rotating back and forth, so here I am rotating back and forth. And I can feel I'm exerting I'm exerting a torque using my back muscles. And I'm clearly accelerating because I go one way and then I rotate back the other. So I speed up, slow down, speed up, slow down. I can kind of gauge how much effort I'm putting into that. What happens if I hold my arms out? Now what this suggests is if we take the very same amount of mass and we move it farther away, the inertia goes up because the inertia depends on mr squared. Now, my arms aren't that much of my mass, but I am taking my arms and I'm moving them out. And you know, this requires a lot more effort. I've taken just the mass of my arms and moved them farther away from the axis of rotation. The axis of rotation here goes right down my back, I guess, right down my vertebrae. What happens if I do the same thing with a book? So this is a few kilograms, and if I hold it close to the axis of rotation, no big deal, not much effort here at all. Now what happens if I hold it out here? Now I have to lift it, but that's not what we're asking about. We're asking when I accelerate, can I tell that there's more of a resistance to acceleration? And there really is. Imagine putting one of these in each hand and rotating back and forth. Rotational inertia goes up based on two things. If there's more mass, in general, there's more rotational inertia. It's harder to rotate an object with more mass. And then it depends on how the mass is spread out. What's the distribution of mass? This is kind of the simplest case where all the mass is concentrated into one object. Now if I had many of those masses, if I had several masses set up here, then what we could do is add all of the mr squareds together to come up with a rotational inertia for the whole system. So let's look at an example of that. Here is example 10.8. I'm calling it rotational inertia. Let's say that we have an axis of rotation here. Maybe this is my arm sticking out here with a textbook in each one. Ooh, 5 kilograms? No, I don't think the text is that much. And one's 7 kilograms. Anyway, the R1s and the R2s are both 2 meters. So I'm kind of in the middle here, but it's not the center of mass because M2 is heavier. In any case, we're rotating around this axis. So rotations don't have to be around the center of mass. We can rotate around whatever point we want. So there's a rigid object holding M1 and M2 together, and the total rotational inertia, according to that formula we derived previously, would be mr squared for object 1 plus mr squared for object 2. We're treating these masses as being concentrated at just one point. So that's 5 kilograms of mass times 2 meters of leverage squared, and 7 kilograms of mass times 2 meters of lever squared. That gave me rotational inertias of object 1 has a rotational inertia of 20 kilograms times meters squared. And object 2 has a rotational inertia of 28 kilograms times meters squared. We can combine those. So if we're rotating this object around that axis, we can just add up the individual rotational inertias. We have a total of 48 kilograms meters squared. Now, as the rotational inertia goes up, we're going to have to push with a bigger and bigger torque to get this thing to accelerate. More inertia means more torque needed to provide the same acceleration. Now, what would happen if we took the very same two objects, object 1, object 2, 5 kilograms, 7 kilograms, but we restructure them? So this time, instead of both objects being 2 meters from the axis of rotation, and here's the axis here, right? That's my axis of rotation. It's the same formula. It's the same masses, but the R's are different. So if we take the same masses and move them closer to the axis, it's easier to make that thing rotate. But if you take the same mass and you move it farther away, that's going to be harder. So we took the 5 kilogram mass and moved it all the way into half of a meter, and look, it went from 20 kilogram meters squared all the way down to 1.5. That's going to be easy to rotate. But look what happened to the other one. We took the 7 kilograms, we moved it all the way out to 4.5. What were we thinking? That's going to require, that's a lot of inertia. That's going to really require a lot more torque to provide some kind of a substantial acceleration. So, you know, if we have a torque, then we're always going to get a little bit of acceleration, even if the inertia is really high. But if the inertia is really high, that's going to reduce the amount of acceleration that we've got for a particular situation. Okay, so that's kind of the introduction to rotational inertias. Now what we can do is we can take this mr squared, which is called the rotational inertia. What if we want to apply this formula to these cylinders? So I got a couple of cylinders here. They're not individual masses. I'm going to have to do some kind of an integration. I am going to have to take these cylinders and divide them up in a way where I can calculate every little dm times r squared. And some of the mass in these is close to the axis, and some of it's farther away. The mass that's farther away will contribute greatly to the rotational inertia. The part that's close in will not create as much rotational inertia. So in this example, they're saying these two cylinders happen to have the very same mass, but will they have the same rotational inertia? And absolutely not, because the cylinder on the left, on average, its mass is farther away from the axis of rotation. So that's what's happening with the comparison here. This is going to have much more rotational inertia than this one does, even though they have the same mass. Now, here is a table of different shapes and how much rotational inertia they have. And notice we've got to pay attention to the axes here too on the table. But let's just take a few of these and look through and kind of get a feel for what's going on with the rotational inertias. Let's say that we take what's called a hoop. So a hoop is a circular piece of material, but it's completely hollowed out. Now, for a hoop, what axes of rotation might we want to look at? And the axes they have listed here, one of these goes right through the center. Now this drawing needs to have that line go through. Oh no, yeah, it does. It needs to have a line go through on one of those. So that drawing maybe. That needs to get connected. So there's an axis that goes kind of through the center of the circular hoop. All the mass is at a distance r. If all the mass is at a distance r naught, then the rotational inertia will be mr squared. Because when I add together, when I integrate over that shape, it's going to have all the mass at the very same value of r. Now notice they've got two thin hoops listed. They've got thin hoop around an axis that goes through the center. But then they go, what happens if we switch the axis, or if we switch the object so that the axis goes through the hoop itself? Now it's rotating in a different fashion, and this formula is different. Okay, now it's 1/2 mr squared, which means only half as much inertia as we had before. And then this term is saying it also depends on the width. So if the hoop is spread out this way, that will add additional rotational inertia. If somehow we had the hoop down so that W was just tiny, negligible, then it would still be only 1/2 as much as the other orientation. So the axis that you pick, or the axis that you're given in a problem, is going to determine how much rotational. So you can't look at an object and go, how much rotational inertia does this have? You first have to ask the question, what is the axis we will use when this object goes into rotation? What axis will it be rotating around? That's a question we have to ask for that. Now, here, the next one down, we have a solid cylinder. That's a common geometry. So we have a solid cylinder, and we assume that the density is the same throughout. Notice that the solid cylinder, compared with the hoop, only has half as much inertia if they both have the same mass. Now notice, it depends on mass, and it depends on how the mass is distributed. So if this one's 5 kilograms and this one's 5 kilograms, and the R values are the same, then this will only have half as much inertia, rotational inertia. And that's because on average, what we're really doing, this 1/2 out here, it's what I consider to be a shape factor. It's a factor that we can calculate using integration. And what it's telling us is, on average, how close is the mass towards the center versus how much of it is spread out. And in the case of the hoop, all the mass is out at R0. With the cylinder, it's a continuum, right? Some of the mass is really close to the axis and has almost no effect on the inertia. Now notice again, they've picked an axis that goes right through the center of mass with a particular orientation. We could switch that. We could run the axis so that it goes from side to side. We could move the axis off to the side here so that it's not balanced. It's not going through the center of mass. You could still rotate. There could still be a rotational axis that would rotate that object. Okay, so we've got solid cylinders, we've got hollow cylinders. Stop momentarily with the sphere too. So kind of the big three that are going to show up in a lot of problems are the hoop, solid cylinder, and solid sphere, uniform solid sphere. And when you carry out the integration here, you get a factor of 2/5. So it's almost like it's a shape factor. If it's a hoop, it gets a factor of 1. A solid cylinder gets a factor of 1/2. A sphere gets a factor of 2/5. So we can see the sphere, on average, has its mass even closer to the axis of rotation than a cylinder. Okay, a couple of other rotational inertias that are going to be important for us. Both of these, the stick, the rod, around its center of mass, or what about the rod along one of its ends? And so if you have, if you have a long stick or a long rod, rotating it around the center of mass is going to be much easier than rotating it around one of the ends. If I rotate it around the middle, there's no part of that stick that's more than half L away from the axis of rotation. But if I rotate around one of the ends, then a lot of the stick is quite a distance away from the axis. You can look at the shape factors here for the center of mass. That's only 1/12 ml squared. For rotating around one of the edges, it's 4 times as much. It is 1/3 or 4/12 ml squared. And then a rectangular thin plate, 1/12 ml squared. So that's like a textbook, right? So if you took a textbook and you rotated it around a central axis that goes through the center of mass, then the rotational inertia is given by the formula we see. So these have all been calculated using integrals. And I don't know that you specifically, maybe you do these in calculus, I don't remember, I'm not familiar with how that works. So here's the whole shape factor thing again. Let's say that we have a ramp, and we have a round object, and we're going to let go and see how fast it comes down the ramp. Now, will all round objects go down the ramp at the same speed, or the same acceleration, I guess is what we should really say? Will all round objects have the same acceleration? Back when we were doing linear motion, if the incline were frictionless, if the incline's frictionless, what we found is that everybody has the same acceleration. All of the objects slide down a frictionless ramp at the same acceleration, independent of how much mass they have. That's not true for different shapes if they're rolling. So what we find is that the hoop has a shape factor of 1. So here, all the mass is around the edge. And the solid cylinder had a shape factor of 1/2. And the solid sphere had a shape factor of 2/5. Who gets to the bottom first? Who goes fastest? And it's the sphere. The sphere has the least rotational inertia. And we'll do this in more detail to show exactly why this happens. So the lower shape factor goes faster. And then as the shape factors get bigger, that slows things down. And you might be thinking, well, wait a minute, what about energy? If they all have the same mass, don't they all have the same energy when they get to the bottom? And that's true. They'll all have the same kinetic energy. But for a hoop, more energy goes into rotation. So the same amount of energy is there. You can recover all that energy, but it doesn't go as fast. And we'll see how that works too. So what I could do is if I'm given a problem and they say part A, solve for the hoop, part B, solve for the cylinder, part C, solve for the solid sphere, and I'd rather not do 3 problems, I'd rather just do 1. What we can do is, for the rotational inertia, plug this formula in. So I use C for whatever reason. Sounds like a constant. It's a shape factor. And so if C is equal to 1, it's a hoop. C is equal to 1/2, it's a cylinder. So we can carry out all the formulas, keeping the shape factor in the algebra. And then we can look at the formulas that we derive and figure out what's going to be different for the hoop, the solid cylinder, and the solid sphere. All right, here is a little bit of rotational dynamics. All right, so back in chapters 4 and 5, we looked at objects dropping from pulleys, and back then we kept saying the pulleys are massless, the pulleys are massless, the pulleys are massless. And what we really meant was we haven't looked at rotational motion yet. So we can't really analyze a pulley in terms of its mass and its inertia until we've looked at chapter 10, and now we've looked at chapter 10, so let's do it. So here's a pulley. There's an axis that goes right through here. So the pulley is on some kind of an axle. There is a normal force holding the pulley up. There is a gravitational force pulling the pulley down. We're hoping that the axle is sturdy enough that the normal force can be enough to support mg. Now, in addition to mg, there's another downward force on the pulley, and that is we've wrapped a rope around the pulley, and we're pulling on it. So there's some kind of cable, and we're pulling on this, and we're pulling on it with tension T. So what's going to happen with this pulley? Is it going to start accelerating? What's going on? So the starting point for this, and this we should highlight too, I guess. We should really highlight this. Remember back in chapter 4, we said it all comes down to acceleration depends on net force divided by mass. And now what we have is the acceleration depends on net torque divided by rotational inertia. So I has taken the place of mass, torque has replaced force, and rotational acceleration has replaced linear acceleration. Other than that, it's the same formula. So it works the very same way. What we can do then is we can ask what forces are acting on this, or what torques. Now, the normal force and gravity, they don't have any lever distance. If the disc, the pulley that we have, is balanced, if it's a uniform disc, then the normal force, the gravitational force, will be acting right at the center, and so it goes right through the axis. There is no torque from mg. There also is no torque coming from the normal force. Now, tension is going to provide a torque. So the tension here is pulling along a direction that misses the axis, and it misses it by a perpendicular distance. We'll call that r, where r is the radius of the pulley. So the torques that we're going to have acting on this, first of all, we're going to have a torque that's r times t. That's the lever distance, little r, multiplied by the tension, T. And then in the problem, I read this one carefully. I probably shouldn't have, but I read this carefully, and they told us, and I think this is from the textbook. and it did not get included in the slides, but I thought it was a really useful example, so I brought it in. They tell us in that problem that there's actually a friction taking place in the hub. So this pulley isn't able to rotate. It's not completely without friction. So we're going to have to include a frictional torque. And that frictional torque is taking place, again, right here in the hub. So I'm going to have a torque tending to pull this down, and then I'm going to have some kinetic friction that's opposing that. Now, for the rotational inertia, we had talked about using a shape factor times mr squared. I'm going to go ahead and do that. Now, they tell us that r, the radius of this, is... Okay, that should have been written down. I didn't get it written down. The radius of this is 0.33 meters, and the force is 15 newtons. When I multiply those together, R times T is giving me a torque of 4.95 newtons times meters. Now they tell us in the problem that the opposing frictional torque is 1.10 newtons times meters. Now, since this is a kinetic friction, it's going to oppose whichever direction the thing starts rotating. So when it starts rotating, the friction is going to be in the opposite direction. And that says that the net torque then is going to be given by 4.95 minus the frictional torque. So we have a net torque of 3.85 newtons per meter. Now, the acceleration that they gave us in the problem, they said that when we pull on this with some tension, it's starting out at rest, and then after 3 seconds we are able to accelerate it all the way to 30 radians per second. So I calculated what the rotational acceleration was, assuming that the forces are constant. Assuming tension is constant, we're pulling on this rope, and assuming the frictional force is constant, then the torques will be constant, and that says the rotational accelerations will also be constant. So I was able to go in and calculate 30 radians per second divided by 3 seconds. I was able to calculate that at 10 radians per second squared is the rotational acceleration that we'll have. So I did this. I took and I'm a little nervous here now because my 385 became 0.395. Somehow that got copied over wrong. The acceleration I got was exactly 10, so this should be 0.385, I think. So this is, oh, I see where the 95 came from here. Yeah, I dropped the 0.10. So what's the easiest resolution here? Maybe we should turn the frictional force into 1 Newton meter, and then this would be 395, and then everything else should be fine. So 3.95 divided by 10 gives us, or 3.95 divided by 10 gives us 0.395. Now that's going to come out in units of kilograms meters squared. So this is going to be in kilograms meters squared. C, the shape factor, is going to be I divided by mr squared. And when I did that, I got a shape factor of 0.907. However, I got to go back and redo it. I wonder if the book used a shape factor of exactly 1. I think what possibly has happened here is the book calculated this based on a shape factor of 1, and I think possibly my miscopying this may have. So take a look at that and see. If we switch this back to 385, what are we going to get on the bottom? Ooh, but that's squared. Yeah, take a look and see. It's possible because, oh no, this is going to, oh, that's going to decrease, right? Yeah, I think the shape factor is just going to go down. Anyway, I was curious, so if a shape factor is 0.907, it's not a cylinder. It's not a solid cylinder. It's actually closer to being a hoop. So this might be a pulley where most of the mass is towards the outside. Maybe there's some spokes or something. This is more like a bicycle wheel shape factor than it would be for a solid cylinder. Just curious what kind of numbers they had given us in that example. All right, here's another good example. Let's put a bucket here. So before we just had this tension, but now we're going to put a bucket. And what that does for us is we have to keep track of the acceleration of the bucket. And that's going to be a linear acceleration. And we have to keep track of the acceleration of the pulley. And that's going to be a rotational acceleration. Now, how are those two going to be related? And the linear acceleration of the bucket, when it's dropping, is going to be equal to r times alpha, where alpha is the rotational acceleration. Now, the rate at which the bucket accelerates downwards is going to match the tangential acceleration, right? I've got this cable wrapped around this pulley, and whatever, okay, here comes the cable. Whatever the tangential acceleration is as we come up and around, that's going to match the acceleration as the cable continues off in this direction. So accelerations at each point along the cable are going to match. And that's why we get to use A equals R times alpha. Now let's do the linear side first. Going back to chapter 4, we can write down a formula for the linear motion. The acceleration of the bucket is going to be equal to mg minus t. mg is in the direction of the acceleration. That gets the plus sign. The tension is holding things back. So I wrote that down, divided through by the mass. And then I also wrote down the formula T equals m, just because it's always been so useful before. So I went in and solved for the tension. Now that's only one formula. I don't know what the tension is, so it's not enough information to determine the acceleration. I am going to have to find out what the acceleration is here, and then somehow bring those equations together. So for the rotational side, instead of linear acceleration, I'm going to use rotational. And remember, the rotational acceleration is going to be torque, that's a torque, divided by rotational inertia. Now, I don't remember if, I think I took out the friction here. I think this problem might have had frictional torques in it too. I took it out. I thought, let's just look at a frictionless setup and see how it works. So that says the only torque that we have over here is T times R. It's the force of tension with a lever distance of R. And so here's the torque divided through by the rotational inertia. I'm going to use that shape factor approach. So I put Cm R squared in the denominator. Now we said at some point we have to relate the rotational acceleration to the linear acceleration. We said that's not that hard. A is just going to be equal to R times alpha. So for the rotational motion, I can calculate the tangential acceleration as R times alpha, and that brings an extra factor of R in. So both factors of R are going to cancel out. And that leaves me with linear acceleration is equal to tension over shape factor times m. And if I solve for tension here, it's shape factor times the mass of the pulley. The masses are not the same here. I got two different masses going on. The big M is the pulley, the little m is the bucket. And then that's equal to A. So I took the two tension formulas and said CMA equals mg minus MA. That's right there. And then I solved it for A. So there are a couple lines of algebra, and here's what we got. So what we got was the acceleration of this system, you know, the linear acceleration of the bucket dropping, and the tangential acceleration along the edge of the pulley is going to be given by mg over m plus shape factor times big M. So how much effect does the mass of the pulley have? Well, it's not the total mass of the pulley that is included, it's the mass times whatever the shape factor is. If that's a solid cylinder, which seems like a good shape factor for a pulley, then C would be 1/2. I would only include 1/2 the mass of the pulley as an inertial effect. So the net force coming from the outside, coming externally, driving this is gravity. So gravity is the only force coming in from the outside. The tensions are actually an internal force. The tension is acting between the two objects. It's acting between the bucket and between the pulley. So once we treat this as a system, the tension has dropped out, and this is what the acceleration is like. Now, let's go back to chapter 4. What would happen if the pulley had no mass? What if the pulley has no mass at all? Well, we just cancel out the mass effect for the pulley. The remaining m's cancel out, and it says the bucket just drops with an acceleration of g. If there's no mass, then there's no tension in the cable, and the bucket will just drop in free fall, is what's going to happen. So this is frictionless. I wrote down at the bottom the friction. I left the friction out because I think it's good to see what's going on here. Now, if there were friction, how would that get added back in? And it would get added back in as a force here. So I put some numbers in. So let's take a look. The little m, let's say, is 2 kilograms. The big M is 4 kilograms. I assumed a shape factor of 1/2. And the R here was 0.33 meters. So I think this is the same pulley in the textbook. You know, once they get one example with one object, they tend to bring it back and run those numbers again. So putting all the numbers in, here we got 2 kilograms divided by, this is the inertia, 2 kilograms of inertia here. The pulley was 4 kilograms, but because it has a shape factor of 1/2, only half of that gets used towards inertia. And then we multiplied by the gravitational field. And that gave us 4.90 meters per second squared. Now let's bring back in the, let's add friction in and see what would happen. If you remember, that would create an additional torque at this point. So I got to subtract off the friction. I still use the shape factor approach. When I got to this step, the r squareds here canceled, but the right side only had one factor of r. So I rewrote that as the acceleration then would be given by tension minus torque over r over cm. So the tension now, instead of being cma, is given by, there's an additional term. So we put the frictional torque back in, and we are following it through to see what happens. So here we are with friction. Now the linear equation didn't change. The friction's not happening with the bucket, but the friction is happening with the disc. So the friction shows up here as torque friction over R. I brought these two together, solved for A, and now here's what we've got for the net inertia. Well, the friction didn't affect the inertia. Friction's not an inertial effect. Friction is a force, and it's a force that can create a torque. And so what we've got is, instead of gravity alone determining what's going on here, now we have a frictional torque that's reducing the acceleration. And I had to take that torque and divide it through by big R. Okay. So that was a number of steps that we went through on that one. It's a good set of steps to go through. getting some practice looking at combining, if we go back to the original setup here, good practice with combining linear motion and rotational motion together. And these were brought together because through the tension in the cable, that's what was causing this effect. So let's see. Let's see if we've got got just a couple minutes here. Let's do this as a last example. We'll come back and talk about it a bit. What we've got here is we've got like a wall, and then we have a stick. Now there's an axis of rotation right here, and so this stick can freely rotate when we let go of it. So what we're going to do is we're going to bring the stick so that it's level. Now there's a normal force lifting up on the stick, and there's a gravitational force here. If we think of this as an axis of rotation, then the normal force doesn't have a lever distance. There will be no torque as a result of that normal force. But there will be a torque due to mg. So what we can do is say for this, there's going to be a rotational acceleration. When we let go, this thing is going to accelerate rotationally. That's going to be given by a torque divided by I. Now, the torque that we have is going to be equal to the force, mg. So I got a force right here. The lever distance on this is 1/2 of the length. Now I've called the length d, and I said this rod has a mass of m. So force, gravitational force, and then the lever distance, 1/2 d. Now the rotational inertia, I looked up in that table, and if we're rotating a stick around one end, then the rotational inertia, it told me, was 1/3 md squared. So this is how much torque I've got. This is the rotational inertia. And to get the acceleration, I can take the torque, divide through by the rotational inertia. What that gave me was 3/2 g over d. So when I first let go of this, I'm going to have this much torque. Now, as it rotates down, the amount of torque is going to reduce. The lever distance is going to drop off. So it's not going to stay at this level. All we're solving for is that first instant when we first let go. Now, what it's saying here, though, is that if I look at different locations along here on the stick, they're all going to have the same rotational acceleration, 3/2 g times d. What about the point on the end? That will have the largest linear acceleration. So the linear tangential acceleration is going to be given by r times alpha. So what we can do then is, for that point at the very end, we can say that all the way out over here, r is equal to d, and so the rotational, not the rotational, but the linear acceleration of that point at the very end is going to be given by d times 3/2 g over d. That's what the alpha value is here. So we're just taking this equation, substituting in a value for r, substituting in a value for alpha. And the alpha works out, the linear acceleration is 3/2 g. It's actually accelerating faster than a gravitational acceleration would for an object. How is that possible? And what's happening here is when you're part of a collective object like this, you have to look at the overall torque and the overall rotational inertia. So what's happening here is there's enough torque that some parts of this stick, as they rotate down, are actually going to get pulled down because they're part of the stick at large. So this end of the stick is going to get pulled down with an acceleration greater than g. Other parts of the stick will be at accelerations less than g. So it's kind of interesting. If you're part of an extended object, your acceleration due to gravity, if you're released like this, could be faster. Again, think in terms of amusement park rides. What could we design from this, right? ooh, this could be a lot of fun. You could get a lot of seats set up along here. And then they're holding this up, and then at some point they get everybody situated, and then they release it, and the person on the end gets an acceleration of, they get pulled downwards faster than a gravitational acceleration. All right, we're out of time for the day, so let's stop there. We'll pick up at next lecture. We've got one more class to take a look at Chapter 10. We're taking a good thorough look at this. That's the intentions. If you guys have questions, stop by and let's get those looked at.